2025 could be an explosive year for researchers.
Now let's go to the United States, where millions of people in Florida are struggling.
Beneath the shimmering turquoise waters off Florida's southeastern coastline, an event of profound geological significance has quietly unraveled. A team of marine geologists, working under a multi-institutional research initiative, detected an anomaly beneath the seabed, a formation that defied existing models of the region's tectonic stability and sedimentary history. The initial discovery was made through high-resolution seismic imaging during an otherwise routine geophysical survey. What they found was startling. An enormous subterranean cavity deep beneath the Atlantic seafloor, accompanied by unusual heat signatures and the unmistakable signs of geological instability. The magnitude and nature of the anomaly were enough for the team to issue a rare red alert, a designation reserved for discoveries with potentially far-reaching and immediate consequences. Before we start, smash the like and subscribe buttons for more updates. The cavity, now dubbed the Abyssal Bloom, stretches across an area estimated at over 140 square miles and plunges to depths that suggest it formed rapidly, possibly within the last several thousand years, a blink of an eye in geological time. But it wasn't just its size that troubled scientists. The surrounding sediments were rich with methane hydrates, which are crystalline compounds composed of methane molecules trapped within ice. These hydrates are stable only under precise conditions of temperature and pressure. The disturbance detected in this region indicated not only destabilization, but active methane seepage into the water column. Methane, a potent greenhouse gas escaping from deep sediments into the ocean and potentially the atmosphere, could contribute significantly to climatic changes if left unchecked. The area surrounding the discovery is no stranger to geological complexity. Florida itself rests on the Florida Platform, a vast carbonate shelf that has remained geologically quiet for millions of years. This seeming calm has fostered a sense of tectonic dormancy, but beneath the surface lies a lattice of ancient fractures, relics from the Mesozoic era when the supercontinent Pangaea split and the Atlantic Ocean began to form. Until now, these faults were thought to be inactive, sealed by eons of sediment. The new discovery challenges that assumption. Embedded within the periphery of the cavity were signs of reactivation, microseismic activity, the slow grinding of rock against rock, and the telltale evidence of subsurface slippage. Adding to the mystery was the detection of an unknown mineral compound lining the inner walls of the cavity. Spectroscopic analysis revealed a previously unclassified silicate composition, indicating hydrothermal activity at levels never before recorded in this part of the Atlantic. Hydrothermal systems typically indicate the movement of magma, or the heating of subterranean fluids through deep crustal interaction, often serving as precursors to volcanic or tectonic unrest. But Florida is thousands of miles from any major plate boundary. The presence of hydrothermal dynamics here raises unsettling questions about whether ancient dormant systems are awakening. Marine biologists who were called to study the anomaly noted another oddity: dense blooms of bioluminescent microorganisms clustered around the methane vents, feeding off the escaping gas. These extremophiles are often found near deep-sea hydrothermal vents, but are rarely seen in this part of the world. Their sudden abundance hints at a shift in the underwater ecosystem, a transformation that may ripple throughout the marine food chain. Any significant alteration in the biology of these waters could have a cascading effect on Florida's coastal fisheries, coral systems, and even its tourism industry, which relies heavily on the health and clarity of these environments. The implications of this discovery extend beyond environmental impact. The instability of methane hydrate deposits is a well-documented precursor to submarine landslides. One of the most concerning possibilities involves the potential for a massive subsea slump. Should the structure of the cavity collapse further, it could generate a significant underwater landslide, displacing thousands of cubic meters of sediment in an instant. Such an event would not only disrupt marine ecosystems, but could also generate tsunamigenic waves, tsunamis spawned by sudden seafloor displacement. Although the cavity lies some distance from shore, simulations conducted by the research team suggest that a worst-case collapse scenario could produce a wave strong enough to reach the eastern seaboard, including parts of Florida's heavily populated coastline. This scenario is not without precedent. The Storegga slide off the coast of Norway some 8,000 years ago triggered tsunamis that reached as far as Scotland. The Florida anomaly bears troubling similarities in scale and composition. Given that Florida's coastal regions are flat and low-lying, even a relatively modest wave could flood vast tracts of land, especially in areas like Miami and the Florida Keys, which already grapple with rising sea levels and saltwater intrusion. The threat posed by a methane-triggered landslide is no longer the realm of distant theoretical possibility. It has now entered the realm of imminent geological concern. Another layer of complexity arises from the possibility of tectonic stress redistribution. As the cavity expands or destabilizes, it may relieve pressure in one area only to transfer it to another. The nearby Bahamas platform and the deeper waters of the Blake Plateau could experience increased seismic activity as a result. While the southeastern United States is not typically associated with strong earthquakes, isolated seismic events have occurred in the past. The 1886 Charleston earthquake, for instance, remains one of the most powerful quakes ever recorded on the eastern seaboard. If ancient faults beneath the Atlantic are being reawakened by this newfound instability, Florida could face a future in which seismic activity becomes a new normal rather than a rare exception. Even more perplexing is the absence of volcanic precursors in this anomaly. Typically, hydrothermal activity and heat anomalies of this nature suggest magma movement, yet no magma chambers have been detected in the vicinity. This raises the possibility of a hidden igneous intrusion, perhaps a deep mantle plume, or an ancient rift system that never fully developed but has remained geothermally active beneath layers of limestone and sediment. If true, it could rewrite the geological narrative of the region. Florida, long considered tectonically tranquil, may sit atop a far more dynamic and volatile system than previously imagined. Geopolitically, the ramifications are considerable. The discovery lies within U.S. exclusive economic zone waters, but its proximity to international waters could spark debates over environmental responsibility and potential claims to undersea resources. The presence of rare minerals also introduces a dimension of economic interest. Some of the elements found in the mineral linings are believed to be essential for advanced electronics and renewable technologies. While it is far too early to consider extraction, the mere existence of such deposits could shift future strategies in marine resource exploration. Coastal communities and policymakers now face an urgent need for updated risk assessments. Existing infrastructure, including power stations, desalination plants, and ports, were never designed with the risk of underwater geological hazards in mind. In light of the red alert, contingency plans are being reevaluated. Emergency management agencies are considering new models of coastal evacuation, while scientific teams race to install a broader array of ocean-bottom seismometers and methane sensors to monitor the site in real time. The speed at which this system is changing demands constant vigilance and cross-disciplinary cooperation. From a scientific standpoint, the discovery also opens up a frontier for exploration into early Earth processes. Some researchers believe the chemical and thermal dynamics within the cavity could mirror conditions that existed during the Archean Eon, when life first emerged. Studying the extremophile organisms and their interactions with newly forming minerals might offer insight into the origin of life itself. In that sense, the anomaly is not just a threat, it's also a profound window into the Earth's ancient past. Public interest in the site has grown rapidly, spurred by satellite images showing strange surface disturbances and discolorations in the water above the anomaly. While these phenomena are largely benign, such as the release of gas bubbles and temperature differentials, they have caught the attention of media and conspiracy theorists alike. Some have speculated about lost civilizations, undersea alien bases, or mythical constructs like Atlantis. While these claims hold no scientific merit, they underscore the cultural gravity of such discoveries. Humanity is deeply drawn to the unknown, and a mysterious rift opening in the ocean floor inevitably awakens both awe and fear. In academic circles, debate continues about how to classify the feature. Is it a caldera, a collapsed methane reservoir, or something entirely new? Naming conventions matter because they shape public policy and research funding. A term like subsurface collapse zone implies passive geological decay, while abyssal geothermal system suggests dynamic processes requiring active surveillance. The semantics are still in flux, but the urgency is not. Whatever the label, the threat is real, and the need for comprehensive study has never been greater. Further compounding the intrigue is the electromagnetic interference noted in equipment passing over the site. Survey drones and submersibles have reported momentary glitches, navigational drift, and data loss. Engineers have yet to identify a clear cause, though initial theories suggest high concentrations of metallic elements or possibly piezoelectric effects from the shifting rocks below. These anomalies have complicated efforts to fully map the interior of the cavity and understand the mechanics of its formation. Until more advanced tools can be deployed, large parts of the phenomenon remain cloaked in uncertainty. Weather patterns in the area have also shown subtle changes. Meteorological stations along the coast have recorded slight but persistent anomalies in ocean temperatures and atmospheric pressure, coinciding with peak gas release periods. These microclimate changes could affect hurricane development or alter current systems like the Gulf Stream, which plays a crucial role in regulating climate along the eastern seaboard. Though no direct causality has been established, the synchronicity of these shifts warrants further attention. The scale and complexity of the discovery have triggered a rare moment of unity among disparate scientific disciplines. Oceanographers, climatologists, biologists, and geophysicists are pooling their expertise to develop a holistic understanding of what lies beneath Florida's waters. The site has become a crucible for collaboration, offering the promise of breakthroughs not only in geology, but also in environmental science and planetary systems. But as much as it represents opportunity, it also demands caution. The forces at play here are vast, slow-moving, and only partially understood. Missteps in interpreting the data could lead to flawed predictions or ill-conceived interventions. As the red alert status holds, the world watches closely. Beneath the surface of one of America's most idyllic coastlines lies a developing story of geological transformation, one that blends danger and discovery in equal measure. What began as a routine survey has blossomed into a revelation that could change our understanding of Earth's deep mechanisms and the vulnerabilities of coastal societies. Florida's underwater secret, long hidden in the darkness of the ocean floor, has finally come into the light, demanding attention, respect, and above all, a commitment to uncover the truth before nature decides to reveal it on her own terms. Since the red alert was issued, the scientific effort surrounding the abyssal bloom has transitioned into an intensive, around-the-clock operation. Mobile research vessels, oceanographic drones, deep-sea autonomous submersibles, and satellite relays now form a growing surveillance network above and around the anomaly. Sophisticated LiDAR and sonar mapping techniques are being deployed to chart its three-dimensional structure in fine detail. The initial assumption of a single collapsed cavity has given way to a more complex hypothesis: a system of interconnected voids and pressure chambers, not unlike an underground lung, expanding and contracting with the slow pulse of geothermal forces deep within the Earth's crust. This revelation introduces a level of dynamism previously unanticipated. Such a configuration allows for episodic pressure releases, potentially explaining the periodic methane surges and corresponding shifts in seabed topology. A phenomenon akin to breathing might be occurring deep beneath the seafloor, a slow, rhythmic release and uptake of subterranean energy and fluids. This new model has inspired comparisons to terrestrial calderas, like Yellowstone, where pressure cycles precede large-scale geologic events. But in this case, the absence of surface volcanism cloaks the system in secrecy, making real-time tracking the only way to anticipate what might come next. Scientists are now focusing on acoustic monitoring. The seafloor emits continuous low-frequency vibrations known as seismic hums. These can act like a stethoscope for Earth's deep interior. Since the detection of the cavity, those background noises have altered in tone and rhythm. New data suggest fluid migration across deep sedimentary layers, possibly through freshly formed fractures. Each of these fractures could represent a potential route for methane or even superheated brine to migrate closer to the ocean floor. Their eventual emergence could trigger eruptions of mud, gas, or hot water, phenomena known as pockmarks or cold seeps. These events, while not catastrophic on their own, could collectively destabilize the broader region. In an unexpected twist, paleogeographic analysis of sediment cores taken near the site revealed a striking pattern. Layered within the sediment are dark bands rich in organic carbon, deposited roughly every 50,000 years. These layers coincide with periods of climatic disruption in the paleo record, including abrupt warming phases and sea level rise. This correlation has given rise to a bold theory. The abyssal bloom may not be an isolated event, but part of a recurring geologic pulse, a deep Earth rhythm that periodically alters the trajectory of ocean chemistry and global climate. If true, the current activity may represent the latest expression of an ancient recurring cycle that humanity is only now beginning to perceive. Further analysis of the surrounding water column has revealed a concerning increase in dissolved methane concentrations over a broad area, several kilometers beyond the immediate vicinity of the cavity. These rising levels are interfering with the buoyancy of submersibles and altering the water's refractive index. More importantly, they are beginning to affect local marine life. Fish species that typically inhabit deeper zones have been spotted at shallower depths, disoriented or dead. Coral polyps in nearby reefs show signs of stress bleaching, likely from the acidifying effects of methane converting into carbonic acid. Such ecosystem disturbances have consequences not only for marine biodiversity, but also for fisheries that sustain local economies. In addition to methane, trace amounts of helium-3, a rare isotope typically associated with deep mantle plumes, have been identified in gas samples. This detection suggests that the anomaly may connect to geochemical processes reaching all the way to Earth's mantle. The presence of helium-3 adds a cosmic dimension to the event, as this isotope is extremely rare on Earth's crust and more commonly associated with lunar and interstellar materials. That it's surfacing here suggests a far more profound source of geological upwelling than initially suspected. It also implies that the region is tapping into reservoirs that haven't been breached in millions of years, perhaps dating back to the formation of the Atlantic Basin. Geophysical stress mapping, derived from satellite gravity measurements and magnetometry, has revealed subtle distortions in Earth's crust that appear to radiate outward from the site. These stress gradients are dynamic, shifting week by week, and indicate that deeper mantle convection currents may be exerting upward pressure on the lithosphere. This activity is influencing the behavior of sediments and faults across the broader Atlantic region. The consequence could be an uptick in seismic swarms or the activation of unknown fault lines, not just near Florida, but across the southeastern seaboard and Caribbean basin. As this subterranean force continues to evolve, so does its potential to disrupt human activities. The Gulf Stream, which flows just east of the anomaly, is under constant satellite monitoring to detect any deviation in its flow speed, salinity, or temperature. The current acts like a conveyor belt for ocean heat, regulating temperatures from the Gulf of Mexico to the North Atlantic. Disruptions to its integrity, potentially caused by gas releases, altered seafloor contours, or rising subsurface plumes, could ripple across climate systems as far as Europe. Even a minor wobble in the Gulf Stream's trajectory might increase hurricane frequency or severity, change rainfall patterns, or disturb seasonal weather cycles along the Atlantic Rim. A new realm of focus has emerged: the acoustic ecology of the region. Researchers studying sonar recordings have discovered an evolving soundscape above the anomaly. Sounds previously unrecorded, deep moaning frequencies, sharp tonal pulses, and rhythmic percussive knocks have been cataloged and analyzed. While many of these are likely natural byproducts of sediment movement, gas escape, and rock shearing, their complexity and variety are baffling. Some of the acoustic signals have even been strong enough to interfere with long-range whale communication and naval sonar operations. Marine mammals known to migrate through this corridor are altering their routes, which could further affect ocean ecosystems in unexpected ways. One especially troubling element of the ongoing event involves a sudden shift in magnetic field readings recorded by research buoys and submersibles. Although Earth's magnetic field naturally fluctuates, localized anomalies of this magnitude are rare. Instruments have documented a significant deviation in magnetic declination, enough to disrupt compass readings and automated navigation software. Some theorize that the iron-rich fluids rising from deep beneath the seafloor are temporarily altering the magnetic signature of the region. Others suggest that piezo-magnetic effects from tectonic stress may be in play. Regardless of the mechanism, any prolonged change in the local magnetic field could have unforeseen consequences for migratory species, satellite systems, and maritime infrastructure. Among the international scientific community, this discovery is rapidly becoming a case study in planetary-scale feedback systems. The intersection of geothermal activity, chemical emissions, and biosphere responses highlights how deeply interconnected Earth systems truly are. This realization has prompted comparative studies with other planetary bodies. For example, Europa, one of Jupiter's moons, also shows signs of subsurface ocean activity and methane emissions through its icy crust. Studying the Florida anomaly may not only inform Earth science but also serve as an analog for understanding extraterrestrial oceans, potentially aiding future missions in the search for life beyond Earth. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on this Florida discovery? What do you think will happen next? We want to hear from you. Thank you for watching and see you next time.